Hey guys, today we're doing chapter 3, section 4, which is on symmetries of graphs. So we basically got a couple different types of symmetries, and I'm sure that you've seen, or you've talked about symmetry before. You had to have. One of the main types of symmetry is symmetry over the y-axis. That is actually called being an even function. We also have other types of symmetry. We have symmetry over any line, really. We have symmetry over the line y equals x. We also have rotation symmetry, so if I rotate a figure, that can be symmetric as well. So the main ones we're going to talk about today are symmetry over the y-axis, rotation symmetry around the origin, and then what it means to be neither. And then we're also going to talk about symmetry over the x-axis as well. So symmetry with the y-axis is basically if you can reflect your function over the y-axis and you get the same thing, that means that it's symmetric over the y-axis. So if for every xy on the graph, its reflection image over the y-axis, which would be the point negative xy, is also on the graph, then you know that it's symmetric over the y-axis. These are also called even functions, okay? And that's going to be important. We're going to talk about that even a lot in this chapter. Okay? So another way to write it is that f of negative x is equal to f of x. Okay? The way that I'm going to talk about it is using these 2 points though. So I know that an even function contains the point xy and the point negative xy. And if you're not really sure, you can kind of draw out an even function. So if I think about this function here, that's symmetric over the y-axis. If I have this point here as xy, which that could be 1, 1. Okay, then if I reflect that, I also get the point negative xy. Okay, so notice that as I reflect that, this x value is the same thing, but it's negative, and my y value is the exact same. Okay, so that's how I know that those 2 points are on the graph. If I want to show that the graph of y equals the absolute value of x is symmetric over the y-axis, what I need to do is a proof. And I'm going to prove it by showing that these 2 points are both on the line. So I'm going to start by plugging in the point xy. Well, if I plug in the point xy, I just get y equals the absolute value of x. If I plug in the point negative xy, I get y equals the absolute value of negative x. So, thinking about that, the absolute value of negative x is actually just the same thing as the absolute value of x, because when I take the absolute value, what I'm doing is I'm getting rid of that negative. So this is actually just the absolute value of x. So now that I've shown that these 2 things are equal, I can prove that this is an even function. Okay? So basically you're just going to do proofs for all of these. Next one I want to talk about is symmetry with the x-axis. There's actually not a name for this. This would fall into the neither category, meaning that it's not even and it's not odd. So if for each point xy on the graph, the point x negative y is on the graph, that would be considered symmetric with the x-axis. So again, I'm just going to kind of show you a little sketch here. If I have the point xy on my graph, so this would be 1, 1, and then I reflect that over my x-axis to get this point, notice that my y value is the one that's changing now, and my x value is staying the same. So this would be x negative y. So to prove something's even, all you have to do is show that these 2 points are on the graph. So show that the graph of x equals y squared is symmetric over the x-axis. Well, I can start by plugging in my xy, and I get x equals y squared. Then I can plug in my x negative y, and I get x equals negative y squared. Well, if I take a negative value and I square it, that negative isn't there anymore. So think about negative 2 times negative 2, that gives me positive 4. So essentially squaring it is getting rid of that negative, so that's actually just y squared. So now that I know that those 2 things are equal, I can prove that this is symmetric over the x-axis. Okay. My next one is symmetry with the origin. So this is that rotation symmetry around the origin. For each point x, y on the graph, negative x, negative y is also on the graph. These are also called odd functions. So that's important. Notice that if you have something that's rotation symmetric around the origin, that's considered odd. So we want to show that the graph of y equals x cubed is symmetric over the origin. Again, let me just kind of draw this graph here. So this is like a cubic function, or y equals x cubed. If I think about the point xy here, and if I think about rotating that 180 degrees around the origin, I would get this point over here. So notice that my x value has been negated, but my y value has also been negated, which is why I get negative x, negative y. So if I want to prove this, I'm going to start by plugging in x, y, and I get y equals x cubed. Then I can plug in negative x, negative y, and I get negative y equals negative x cubed. Well, if I cube a negative number, it's still going to be a negative number. So this is actually just negative y equals negative x cubed. Okay, then what I can do is I can just divide by negative 1, and I get y equals x cubed. So now I've proven, since these two things are equal, that this is an odd function. All right. In general, if f is a function and each point x, y on the graph is mapped to x plus h, y plus k, then the graph of the image is congruent to the graph of the pre-image, and all key points and lines are also mapped under this translation. Specifically, lines of symmetry, maxima, minima, vertices, points of symmetry, and asymptotes are all mapped. So essentially, whenever you have some sort of translation for any of these types of functions, all the key points of that original function are mapped using the same translation. So let's say, for instance, I know that I'm adding 3 to my y value, meaning I'm moving it up by 3. Well, if my original vertex was 0, 0, and I'm just moving it up by 3, my new vertex would be 0, 3. So basically, you can think about these translation images using the lines of symmetry, vertices, points of symmetry, any of those points, you can just use the same translation to figure out what your new graph is going to look like. Okay. Also, please be really careful when you're doing these proofs. You really do need to show every step, even if it might seem obvious. They're proofs. So proofs, you really need to show things even if you think they're obvious. It's really important to pay attention to detail in your proofs. And that's everything for section 4.